We will now begin section 3.2, where we will discuss linear and quadratic functions. We'll begin by looking at the definition for a linear function. A linear function, say f, of one variable, say the variable is x, is any function that can be written in the form f of x is equal to mx plus b, where m and b are real numbers. If m is not equal to 0, f of x is equal to mx plus b is also called a first-degree function. As you recall, we have already spent some time discussing linear equations. Remember that when we talked about linear equations, we said that they could be written in what we called slope-intercept form, which was y is equal to mx plus b. The change that we are making as we move into this section is that we are now calling this a linear function. And so we are replacing the y with an f of x. So our linear function will look like f of x is equal to mx plus b. M remains to be the slope, and b is the y-intercept in both cases. I remind you that a linear function or a linear equation is one that only has exponents no higher than 1. And oftentimes we don't see that exponent at all because on the x, if it's to the first power, it is typically omitted. That is what we're talking about when we say that it is a first-degree function. We're saying that the exponent is 1. So one thing that we are asked to do with our linear functions is to graph them. Now again, we have already graphed these functions as linear equations. And so our process does not change much because it is a function. Our first function is f of x is equal to 3x plus 2. So keeping in mind what we know about this function, we know that the slope is the number that sits in front of the x. So the slope is 3. And we know that the 2 is the y-intercept. So we know that it has the point where x is 0 and y is 2. And so with that information, we can draw our graph. We can plot the point 0, 2. Then we can use the slope to find the next point. Remember that the slope is technically 3 over 1. And remember that the formula for slope is that it is rise over run. So if we leave our first point and we rise 3 units, that means that we need to go up 3 units. So I'm going to count up 1, 2, 3. Our run is a positive 1, which means we need to move to the right 1 unit. When we do that, we can place our next point. Connecting those 2 points would give us a graph for the linear function. Another option to graph the linear function would be to do a table of values, finding 2 points and then connecting them. For part B, we're asked to graph g of x is equal to 3. Again, this is equivalent to a linear equation that says y is equal to 3. And we have talked about the fact that if we have a linear equation that only has one variable, that it is either a vertical or a horizontal line. If that one variable is a y, we know that it is a horizontal line. So we can go to our graph, and at y is equal to 3, so 1, 1, Here's our origin. So 1, 2, 3. Then we can draw our horizontal line at 3. So you can see that our technique does not change much depending on whether we have a linear equation or a linear function. We're now going to look at quadratic functions. A quadratic function is called a second-degree function because it has a squared term in it. Is a function that can be written in the form f of x is equal to ax squared plus bx plus c, where a, b, and c are real numbers and a is not equal to 0. So for example, a quadratic function might look like f of x is equal to negative 3x squared plus 5x minus 7. In this case, the a value is negative 3, the b value is 5, and the c value is negative 7. When you graph a quadratic function, it graphs a parabola, which is a U-shaped graph. That graph will either open up, as the one in the picture does, or another possibility is that your quadratic function will open down. In either case, there is a point either at the very bottom of the graph or at the very top of the graph where the graph changes direction. In other words, if I were to trace this graph, it goes down, and then when I reach this point, it starts to increase. Similarly, here, if I'm tracing the graph increases, and when it reaches the point, it begins to decrease. That point where the direction changes is referred to as the vertex of the graph. So here is our definition for vertex. It says that there is one point, known as the vertex, where the graph changes direction. Scanning the graph from left to right, as we did, tracing the graph from left to right, it is the point where the graph stops going down and begins to go up, or the graph stops going up and begins to go down. Every parabola is symmetric with respect to its axis. A line passing through the vertex dividing the parabola into two halves that are mirror images of each other. This line is also called the axis of symmetry. So let's go back to our picture for a second. What we're talking about when we talk about the axis of symmetry is a line that cuts the parabola into two equal parts. So on this graph, the axis of symmetry is going to come straight down the middle. The axis of symmetry will always pass through the vertex. And it produces mirror images. It produces the left side of the graph being a mirror image of the right side of the graph. And this is called your axis of symmetry. Similarly here, your axis of symmetry would sit right here, cutting the parabola into two parts that are mirror images of each other. The next thing that we're going to look at is the vertex form of a quadratic function. If a quadratic function is in vertex form, it is very easy to read off what the vertex of the parabola is. So our slide says that the graph of the function g of x is equal to a times the quantity x minus h squared plus k, where a h and k are real numbers and a is not equal to 0 is a parabola whose vertex is at hk. So what this is saying is that if your parabola is in this format, then your vertex is going to be the point hk. So you can pull off your value h and pull off your value k, and you'll have the vertex of the parabola. The parabola is narrower than your regular graph of x squared. Okay, so we're saying more narrow than this graph if your a value, or technically the absolute value of that, is bigger than 1. And it's wider or broader than your original graph if your a value is between 0 and 1. The parabola opens up if a is positive and down if a is negative. And so there's a lot of information right there. We're going to look at an example and try to talk through that information. All right, so let's say that our problem that we are given is f of x is equal to negative x squared minus 2x plus 3, and we're asked to locate the vertex and the x-intercepts. Now, one thing that I'm going to go ahead and point out is this last statement here that says the parabola opens up if the a value is positive and down if the a value is negative. So right now, as I look at this, I note that the a value, the number sitting in front of the x squared, is a negative 1. And since that is a negative number, then I know that my parabola should open down. If it had been a positive number, it would have opened up. I also know that since my value is, the absolute value of my a is equal to 1, that it is going to have the same width as this basic graph. It's not going to be any wider and it's not going to be any more narrow. So I'm going to make that note as well. So no wider or narrower than your basic graph. Okay, so now that we've noted those two things, let's look at what the problem is asking me to do. I want to begin by putting this equation into the format so that I can read off the vertex. So I want to try to write it as a times x minus h squared plus k. And the way to do that is to complete the square. So I'm going to take my function here. And remember that in order to complete the square, you have to have a 1, a positive 1, sitting in front of the x squared. So the first thing that I'm going to do is I'm going to pull that negative 1 in front of the x squared out of the first two terms. And I'll leave the plus 3 tacked on the end. So if I take a negative 1 out of a negative x squared, that's going to leave me x squared, because I know negative 1 times x squared is negative x squared. And if I take a negative 1 out of a negative 2x, that's going to leave me a positive 2x. Now, I want to complete the square. So recall that in order to complete the square, you want to take your middle term, which has a coefficient of 2, and you want to multiply that by a half, and then square the result. So half of 2 is 1, and 1 squared is 1. And so I'm going to add 1 to both of those. I'm going to add 1 here, and I'm going to turn right around and subtract 1 here. And in doing so, I don't actually change the problem because I have added 1 and I have subtracted 1. Now, I do need to keep in mind, and I need to be careful here, that this positive 1 that I added is going to get acted upon by this negative 1 on the outside of the parenthesis. So what I'm saying is that when I multiply this negative 1 back through, I want to be careful with what I just did. Negative 1 times x squared is negative x squared. Negative 1 times 2x is negative 2x. Negative 1 times positive 1 is negative 1. So I actually, in this part, have already subtracted 1. So in order to keep it balanced, I do need to add the 1 on the other side. Okay, so once that is done, then I am going to factor this part right here. So I know it's going to have to be x and x. I know that to make the 1, it's going to be 1 times 1. And because there are pluses all the way through, I'm going to do 2 pluses here. And I'm going to go ahead and say 3 plus 1 is 4. So I have negative x plus 1 squared plus 4 as my function, which sits in the vertex form. Okay, so let's look back just a second at the vertex form, and let's make sure that we are right. We're supposed to have an a value in the front, an x minus h squared on the inside, and then a plus k. Okay, so let's go back to our problem. And I'm going to write that down over here so that we can be sure that we are setting this up correctly. So let's check. We've got an a value because we have a negative 1, so that's not really going to be a problem there. Okay, the parenthesis part is supposed to be x minus something. So let's rewrite that. Instead of x plus 1, let's rewrite it as x minus a negative 1. And then we're supposed to have plus a k value, which we do. All right, and remember that your vertex now will be the h and the k. So your vertex here will be the h value, which is negative 1, and the k value, which is 4. The problem also asks me to find the x-intercepts. So let's do that as well. So how do we find the x-intercepts of a problem? To find the x-intercepts, remember that you're going to set the y value equal to 0. So we're going to take our function negative x squared minus 2x plus 3, and we are going to set it equal to 0 because remember that your y value is your f of x. So instead of f of x, I'm going to put in a 0, and then I'm going to look at solving this expression. So in order to solve, we're going to first deal with this leading coefficient of negative 1. So I am going to divide each term in the problem by a negative 1. I know that things are easier to work with if I don't lead with a negative 1. So that's going to give me 0 is equal to positive x squared, positive 2x, negative 3. And my hope is that this is going to factor. So I know it has to be x and x because x squared would make x times x would make x squared. The only way to make 3 is going to be to multiply 3 times 1. And I need the 2x, the middle terms, to combine to give me a positive, which means that the 3 needs to be positive and the 1 needs to be negative. Now, if your factoring is weak here, you would want to check this by foiling it to be sure that your signs are in the correct place. So now we can set each of those terms equal to 0, which tells me that I have an x-intercept at negative 3, and I have an x-intercept at 1. So my x-intercepts would be the point negative 3, 0, and 1, 0. Now, we can easily, with that information, graph the equation of the parabola. We know the vertex is at negative 1, 4. So we can plot that. So negative 1, 1, 2, 3, 4. There's my vertex. We know the x-intercepts. We found those to be the points negative 3, 0 and 1, 0. So 1, 0 is here. 1, 2, 3. Negative 3, 0 is here. We know the parabola opens down. And we know that it has the same width as the original. So with that information, you can come in and sketch the graph of that parabola.